participants, pop out chat, toggles timestamps. So it says I'm now live. And when I click the three dots, it says pop out chat, toggle timestamps, and participants. And that is all it says. Participants. No, it just lists the participants though. It doesn't show me a link. It's top chat, live chat. So let's go to live chat. No, the three dots only show me participants, pop out chat, and toggle timestamps. It says, so it does, the web address to which I'm streaming is youtube.com/webcam question, and then it has AR, but there's no like long address. There's no. Oh wait, I found it. I think so. Let me show it. Can I give it to you and you can test it real quick? https://youtu.be/ it looks like a dash, capital E, capital B, lowercase v, lowercase j, capital K, capital E, capital X, lowercase I, capital Q, and then the number 4.
You said there's a dash before that?
It looks like a dash. It's either a dash or a tilde. It looks like a dash.
I'm getting video unavailable. Let me try out that. What is
A tilde, one of those little no, it's not. It's a it looks like a minus. No, it's a minus sign. It's minus capital E. So it's youtu-be / dash, and then capital E, capital B, lowercase v. Actually, I can just test it myself. I'm being an idiot. I'm wasting your time. Oh, it's working. I think it's working. Yes, I got it. No, if you figure it out in the future, let me know.
Oh, it's working. I think it's working. Yes. I got
You're the best. Thanks.
No,
Bye-bye.
if you figure it out in the future, let me know. Oh, it's working. Yes. I got You're the best. Thanks. Bye-bye. If you figure it out in the future, let me know. Oh, it's working.
Welcome. I see 5 of you percolated in. Welcome. Sorry about the difficulty. 4 of you now, but that's okay. Hopefully more and more will come in. So first, I apologize for the technical difficulties. Apparently beyond my control, as smarter people than me were not able to figure this out. But I appreciate your having sticking with me. And I will keep an eye on the chat to the right. I will do my best to record this. I have absolutely no idea if the recording is going to stick or not, but apparently YouTube is doing some cool stuff today. And so I'll do my best to keep everybody on a reasonably strict time limit. All right. So again, thanks for your persistence. We're up to 6. That's good. The first question I'll start with is, can I discuss the format of the exam? That's a righteous question. So the answer is, yeah, I can. There are, I believe, a total of 11 or 12 questions, but they have multiple parts. It is not a multiple choice test. It is short answer, short essay. There's nothing long. There actually is one which has 3 different small paragraphs you'll have to write. Typically, the time taken for students is somewhere in the hour 15 to hour 45 minute range. I think they're allowing 2.5 hours, which should be more than is necessary, but more than that should be enough. You do not need calculators. I'm told actually that we're not supposed to have calculators because most people don't have regular calculators and people use phones and they don't want people using phones. So I've written the exam. While there are some calculations that you can set up, there's nothing you actually need to calculate. Estimating is fine. There will not be any points lost for estimation of mathiness, so don't sweat that piece. But it is not multiple choice. The best example really are the problem sets, and we'll go over a couple of the questions that you all had from problem sets that you sent me. But if you go through the style of the problem sets, that's probably going to be as close to the exam as anything that you have seen. So that's the format. Looking at other question-related things. Can I get a list? Somebody asked, can I get a list of all pertinent and testable learning objectives? And unfortunately, that's the list of learning objectives that came with the lectures. So I have nothing else that I'm going to test. Now, presumably, some of the learning objectives are broader in scope, meaning that they'll ask for your ability to review a whole article. I promise I'm not going to ask you to review a whole article on the exam. I may ask, much like in the problem sets, where I give you a portion of an article, part of the method section, or maybe a chart or table, and ask you to interpret that or specific questions related to that. But nothing as broad as possibly the last learning objective in some of the lectures, where I say, hey, be able to interpret a whole paper. That's going to be beyond the scope. But there may be cases where I give you a method section and ask you to identify a most likely source of bias or subtype of bias. I may ask you to, as they will on the boards, explain whether this study is a case control or cohort or this and that. But again, all within the scope, I think, of what the problem sets did. Okay, one more question generally related to content, and that is, can I get an answer? Can we possibly get an answer key for problem set 2 from the small group? We skipped over some questions in our group, and I don't have the complete notes on everything. I'm happy to take a look at that. I didn't actually write problem set 2. That comes from Dr. Tigas. I think he actually preps the advisors live. I don't think he has written anything out. But if you have specific questions related to problem set 2 and you want to pop them up in the chat, I'll happily try to answer those. All right. Somebody sagely asked a question about pulmonology. I'll not waste your time on this. I think they were trying to be clever. And while I'm always happy to talk about lung medicine, we're not going to waste your time on that today. Okay. One of the questions that I've been asked to comment on relates to problem set 4. I apologize for the reflection of my glasses, but when you get old, you get blind. Can I please explain why if one study has a higher relative risk than another, that does not necessarily mean that they have an higher absolute risk difference? That's actually a great question, and I'm happy to address that. So relative risk and absolute risk difference tell you two different things. And an example I gave in class, which I thought was germane, is let's say I give you a choice between 2 medications, both of which are good for blood pressure. One doubles your risk of lung cancer, and the other quintuples your risk of pancreatic cancer. Which of those medications, both of which have side effects, which of those medications would you rather have? Now, if you don't know anything about lung cancer, pancreatic cancer, you'd say, well, shoot, I'd rather have a doubled risk of something bad than a quintupled risk of something bad. That is intuitive. That makes sense. But in case you don't know already, lung cancer is fairly common. It's not super, super common, but it's a fairly prevalent condition. A lot of people die of lung cancer. Pancreatic cancer is very, very rare. And so because the baseline risk of lung cancer is fairly high, let's say it's 2%, doubling it to 4%, that's a significant difference. The baseline risk of pancreatic cancer is probably 0.01%. If I quintuple that to 0.05%, the absolute difference in that is only 0.04%. So I can relatively increase the risk of a very, very uncommon event, like winning the lottery, like pancreatic cancer, and still it doesn't move the needle much. But modest increases in an event that's very common, like lung cancer, like cervical cancer, like breast cancer, like high blood pressure, even if I only increase the risk of one of those things by 5 or 10% relatively, it's still a big jump in absolute number. So a relatively small increase in risk, relative risk, for a common event can be a huge absolute risk difference, whereas a large 5-10-fold increase relatively in an uncommon event doesn't increase absolute risk difference that much. So while relative risk is an important concept, understanding baseline risk is critical to understanding how important it is. Small relative risk bumps in common events are more significant than large relative risk bumps in super rare events. And that's why two studies which show different relative risks, assuming different relative risks of different baseline phenomena, may have disparate results in absolute risk difference. Higher relative risk does not necessarily mean higher absolute risk difference compared to a lower relative risk. So hopefully that understands. Again, feel free to type in the chat if that was not did not make much sense. All right, moving down, and I'm probably going to tackle these in an order that's going to be different than the order in which we covered them in lecture, but moving down the list. The next question I'm asked is, can I please explain why a relative risk of 1 cannot be the result of type 1 error? So good. Let's talk about what type 1 error and type 2 error are. Dr. Tigas talked about this during the week I was away, but what he probably said, having listened to Stefan talk several times, is that type 1 error is when you mistakenly think that one thing is different from another. That's the way of remembering it. So type 1 is you mistakenly think that one thing is different from another. Type 2 error is when you mistakenly think that two things are the same. Okay. So if you have a relative risk of 1 in a study, you have concluded that two things are the same. Okay. It cannot be a type 1 error, because a type 1 error necessarily means that you've thought there's a difference between two things. That's the definition of type 1 error. Now, again, just because you conclude two things are different doesn't mean you've made an error. But if you conclude two things are the same, which is what this question is asking me, if the relative risk is 1, you're concluding that two arms of a trial are the same. That cannot be the result of a type 1 error, because a type 1 error by definition is you've mistakenly interpreted them to be different. Okay, so that's why a type 1 error cannot be, the relative risk of 1 in a study cannot be the result of a type 1 error. Similarly, if you have a relative risk of 10 or 20 in a study, assuming that's probably going to be statistically significantly different with that huge a difference, that's not likely to be the result of a type 2 error, because a type 2 error is mistakenly concluding that things are the same. So if your two arms of the study are markedly different as a result of a large relative risk difference or a large absolute risk difference, it's very, very unlikely that that will be the result of a type 2 error. Okay, so that's the answer to that question. All right. Can I go over what absolute risk, relative risk, and number needed to treat mean in terms of what you get when when you get a number and how to phrase what that number represents? Okay, so let's tackle this one at a time. So relative risk is basically the percent increase or the times increase in risk in group 1 versus group 2. So let's use a concrete example. If I have a relative risk of 2.5 in a study, it suggests that one group has a 2.5 times the risk, has 2.5 times the risk of the other group. Okay, so that's relative to the other group. So if you have a 5-fold relative risk or a 5 relative risk, the implication is group 1 has a 5-fold risk of the outcome of interest compared to the group 2. Okay, all right. So absolute risk difference is not a percentage, it's an absolute number. So your absolute risk difference is going to not be a percentage or a number. It's going to be number of cases per year. So your absolute risk difference will be, because it's instead of a division or relative risk, you divide the numbers by each other, so the units drop out. But an absolute risk difference, you add or subtract, so the units persist. So when you talk about absolute risk difference, you have to have a unit on that. So an absolute risk difference might be 100 cases of pancreatic cancer per 1,000 patients per year, something like that. And so when you report that in this trial, that's what you'd have to report, is this very long unit for it. So the absolute risk difference between arm 1 and arm 2 of a trial led to an increase in cases of, turn that down so you don't have to look at the blinding light, an absolute increase in risk of the cases of lung cancer per 1,000 people per year. So that actually has to have a unit on it, whereas relative risk won't. Number needed to treat is simply the inverse or the reciprocal of absolute risk difference. So if you take that absolute risk difference and you simply flip it, it gives you the number of people needed to treat. And that's a much more grokkable concept, because you can say to a patient, look, for every 100 people I treat with this medication, I will prevent 1 case of lung cancer each year. That's a much more understandable number than the much more esoteric absolute risk difference. That said, they tend to report the same value. They just do it in a different fashion. Generally, I think people prefer, just from talking to patients, the number needed to treat, although, again, it does provide the same information as an absolute risk difference. All right. Can I briefly review what it means for a confounder to be associated with both the exposed and the outcome groups? Okay, so let's dig into confounding a little bit and talk about what the requirements are for a confounder. So a confounder, again, is a third variable, something that is not the exposure of interest, something that is not the outcome, but a third variable that confounds, that affects your ability to measure the relationship between the exposure and the outcome. Okay. In order for something cannot be a confounder if it is equally balanced in either of the subgroups of interest, meaning if your exposure and your non-exposed group, those are two different groups in your study. If your exposed and unexposed groups have the same exact prevalence of the confounder, it cannot confound the study. So let's say you think that smoking is a confounder between exposure and outcome. I'll leave those things vague. If you think smoking is a confounder between exposure and outcome, one of the ways that you, in designing a trial, can minimize its possible impact as a confounder is to ensure that the same number of people who are exposed and unexposed to exposure of interest are smokers. Okay? When you enroll subjects in your trial, if you ensure for every smoker in your exposed group, there is a smoker in your unexposed group. And for every non-smoker in your exposed group, there's a non-smoker in the unexposed group. That means that the prevalence of smoking in your exposed and unexposed groups are equal. If that's the case, smoking cannot be a confounder. So even if it biologically wants to try to be a confounder, it can't be in your study because of the way you've designed it. Okay. Similarly, in a case control study, if you're looking at an outcome of interest, if you ensure that the same number of people with the outcome of interest are smokers versus those without the outcome of interest are smokers, it cannot serve as a confounder. So when you design a study, a way you can eliminate confounding, you don't even have to mathematically adjust for it, eliminate it, is to ensure that the number of people with that confounder of interest is the same, or the prevalence of that confounder of interest is the same in both arms of your study. If that's the case, it cannot possibly be a confounder. Okay. One of the ways that you can check when you're reviewing a study is say, well, I think smoking might be a confounder. You can look at the prevalence of smoking in both groups. If the prevalence of smoking in both groups is the same or very close to the same, it's unlikely to be a confounder. Okay. The same thing can be done in the outcome. If you look at both people with and without the outcome in a study that you're reading, you're like, well, could smoking be a confounder there? If there's a similar frequency of smoking in the outcome and non-outcome groups, it's unable to be a confounder. Something can only be a confounder if it is imbalanced in the exposure groups and if it's also imbalanced in the outcome groups. Now, just because it is imbalanced doesn't necessarily mean it is a confounder. And I showed you mathematically how you can try to figure that out by creating daughter grids. And I'm happy to go over that later. By creating daughter grids and then seeing what the relative risk is in the parent grid and the two daughter grids. But if the variable of interest, this confounder of interest, is equal in either the exposure and unexposed groups or equal in the outcome and non-outcome groups, it cannot be a confounder in your study. That's why it's important to know this. And again, that might come up on the test where you want to sort of look and see if something can possibly be a confounder or not. All right. I'm going to skip over problem set 3 for a minute. I will come back to it because I actually have to pull up problem set 3 so I can give you an explanation for problem set 3. What are important factors for subject recruitment? Well, the answer to that question is it really depends on the study of interest, right? If you're looking at a cohort study where you're going to have to track people over time, clearly you want to get people who you're going to be able to track over time. You want to make sure that they're going to be able to provide data and make sure they'd be able to give you information regarding the exposure of interest, that they're trackable over time, that you're going to be able to track the development of the outcome of interest. You want to make sure that they're at risk for the outcome of interest. So if you're looking at a breast cancer study as an obvious example, you probably don't want men in that study, although men do get breast cancer to a much lower rate than women. You want to make sure that they are that they don't already have the outcome of interest. So if you have people with a history of breast cancer, you probably don't want them in your breast cancer study. At the end, though, a lot of your decision to determine who comes in a study depends on what you want the study to who you want the study to be relevant to, because you're looking for generalizability. Right? Generalizability is an important aspect of a study. If you're looking at it, if you decide to restrict your study to 50 to 60-year-old men and women, it may not be relevant to 75 and 80-year-old men and women. Now, that said, you might choose to exclude people who are 75 and 80 from your study if you're planning to track people over 10 years, because you may be concerned they'll die of competing causes over 10 years. So you may choose to exclude people from that study just from a trackability standpoint, but understand while that improves your validity, you're going to follow people over time. You're not going to lose them, so you won't have to worry about loss to follow-up. It limits generalizability. Oftentimes, things that increase validity, tight groups, decrease generalizability, which you can't apply to broad groups. So what are the important factors for subject recruitment? The answer depends on the study you're interested in. And let's say you're doing a case control study. In a case control study, recall is really important. So you probably want to ensure that people have good memories. Not that that can be easy to test, but you probably would want to exclude people with issues with dementia, for example. All right. So skipping the problem set ones, I promise I'll come back to them. A lot of questions on problem set 3, question 6, which I know is the TB question. Can I explain? There are 2 other questions I can get to before we go to the problem sets. And I apologize for bending down and having the shine off my head is probably problematic for you. Sorry about that. Can I go over intention to treat analysis? Let's start with that. So intention to treat analysis is an analysis done which says that every subject that you randomize into a randomized controlled trial is analyzed into the arm which they were randomized. Even if they decided to drop out of the trial, even if they decided not to take the, let's say you randomize somebody to medication or a placebo and they decide, I don't want to take it, so they just stop taking pills. Well, in theory, then they're effectively taking nothing. So shouldn't you drop them from the study? And the answer is no, because by retaining them in the study, one, you ensure that you don't induce a selection bias. Remember, selection bias occurs when your study is studying a population that's not representative of the population as a whole, of the Earth's population, of the treating population. Some percentage of people that you give a medication to in the real world are not going to take that medication. You don't necessarily know who that's going to be when you prescribe the medication, when you see the patient in clinic. Sometimes you can have a suspicion, but generally you don't know for sure. So what you don't want to do is exclude subjects who choose not to take medication from your study, because if you do, A, it's not a representative population. B, remember the group that tends to stick with medications that you give them, sticks with recommendations their doctor give, also tends to do good things in other ways. So people who stick to your advice also are less likely to continue smoking, are more likely to be exercising regularly, are more likely to be taking other medications they should be taking. So as a result, the group that sticks with the recommendations of a trial are going to be healthier on average than the people who don't. It's a selection bias. It's not a terrible one, but it affects the ability to generalize your study results. So that's the important part of an intention to treat analysis. Once, again, the easy mnemonic, because it just rhymes, once randomized, always analyzed. Does that increase the likelihood of your making a type 2 error? Remember, a type 2 error is mistakenly assuming that two things are the same. Sure, if everybody in your trial, or if a large number of people in a trial decide they're not going to take the medication that you recommended to them as a part of the trial, then effectively they're taking nothing, which makes them look the same as a placebo group, potentially. And so as a result, the two groups are going to look alike. Even if your medication is super effective, if only 5 or 10% of the population you randomized to take the medication is actually taking it, 90% of the population isn't, and it's going to make them look exactly the same as the placebo group. So as a result, you'll make a type 2 error. So the downside of an intention to treat analysis, while it improves the generalizability of your study, is it increases the likelihood you're going to make a type 2 error, because the two populations, part of your intervention population that's not getting the intervention will look a lot like your non-intervention population, and will again drag the groups closer to each other. So that's the potential downside of an intention to treat analysis. What some authors will do is they should always publish an intention to treat analysis. When you do your research and discovery phase, please always publish an intention to treat analysis. But what some authors will do is they'll publish a per protocol analysis. Per protocol analysis says we're going to exclude subjects in the second analysis who didn't stick with the protocol. We're only going to include people who stuck with the study to the end, were able to take their medication in its entirety. And as a result, I'm going to give you two results. You're going to get the intention to treat result, and you're going to get the per protocol result. Unsurprisingly, the per protocol result often shows us, well, sometimes may show a positive study result when the intention to treat did not. What does that mean? Well, it means that, if people stick with the intervention for over, long periods of time, it will make a difference, or it seems more likely to make a difference. But again, you have to recognize there's a selection bias in there. By including only healthier people in your intervention group, because you've excluded the sick ones who stopped taking the medication, it may make the intervention look like it's doing some good, when at the end of the day, it's actually not the intervention that's doing anything. It's the fact that your intervention group is now consisting only of people who chose to stick with your recommendations. And as a result, that's what's making them look better. It's not the intervention at all. It's the selection bias. So both of them have value, but authors should never fail to report an intention to treat analysis. That's considered the standard of practice, and for good reason. Doesn't mean you can't do the other one, but when you as a consumer of the literature look at both, you want to try to figure out, is the only difference between the intention to treat and the per protocol that they stop taking medication, or are these per protocol people somehow different in another way that might explain the results other than by virtue of the actual intervention? Can I explain confidence intervals related to standard error of the mean? So they're not super related, is the answer to the question. So a confidence interval is, in English, a 95, what you should know, because it's the most common, is a 95% confidence interval. A 95% confidence interval is the number of times, if you give a 95% confidence interval, it means that if you repeated your study 100 times, understanding that there's going to be some random error, 95 times out of 100, you would get a study result within the bounds of that 95% confidence interval. Okay. So again, once more, if you report a 95% confidence interval, it means if you repeated the study in the exact same way 100 times, 95 times out of 100, the result you would get from that repeat study would be within the bounds of that 95% confidence interval. Conveniently, another way to use the 95% confidence interval is to look and see if it overlaps the null. So if you're reporting a relative risk and your 95% confidence interval does not overlap the null, meaning a relative risk of 1, it means your study is statistically significant. So if your confidence interval, let's say the study result is a relative risk of 0.6 with a confidence interval of 0.3 to 0.8, even if I don't tell you a p-value, you know that's statistically significant. If I tell you a study has a relative risk of 0.7, but the confidence interval is 0.2 to 1.3, now you know that result is not statistically significant because the 95% confidence interval includes the null. Again, the same is true on the high side. If I give you a study with a relative risk of 8, the confidence interval, 95% confidence interval is 3 to 11, statistically significant. 95% confidence interval 0.9 to 12, not statistically significant. So there are two ways to use it. One, you can report what it means in terms of repeating the study 100 times. Two, you can look and see if the confidence interval does not include the null, it means the result of the study is statistically significant. You can't say with certainty what the p-value is, although clearly the closer that 95% confidence interval gets to the null, the closer that p-value is going to be to 0.05. So that's the confidence interval. Standard error of the mean really is an issue of sampling and sampling a population. So I guess they both kind of deal a little bit with random error. But standard error of the mean really refers to sampling issues. And if you sample the population multiple times, the likelihood you'd get errors. Now, again, they don't typically report a 95% sampling error. It's typically used as almost like a standard deviation. When they report a sampling error of 2, it means effectively the standard deviation of the samples is 2. So they're similar in as much as they both kind of relate to random error, and they're similar as much as they both present a range of data. But confidence interval is the likelihood that the likelihood the study would be showing reproducible results, whereas a standard error is actually measuring variability of a specific metric in a certain population. So there's maybe a slight bit of overlap there, but I probably wouldn't often use them in the same sentence because I think they mean different sorts of things. Okay. For incidence rate, do we want to always put it in the format of X over 1,000 person years? So again, incidence rate is one of two types of incidence. Two types of incidence: cumulative incidence or incidence rate. Cumulative incidence is reported as a percentage over a given period of time, 10% over a year, whereas incidence rate is always reported with a denominator of person years. Now, it doesn't have to be 1,000 person years. It could be 10,000 or 100,000 or 1,000,000 person years. In theory, you could do it also as 1 person year. There is no standard. 1,000 seems to be a nice round number, so it's probably the one I use most often, and it may well be the one used most often in the literature. But for super rare events, they usually authors usually like to have the numerator be at least 1. So 1 case. And if it's a super small numerator, it's more likely that they would report 1 case per 100,000 person years than 0.01 cases per 1,000 person years. But there's no fixed denominator in that. The key is it is cases per person years. That's the one thing you need to know, is that the denominator in incidence rate will always be person years. All right. So those are the questions that are not directly germane to problem sets. I'm going to go over a couple of problem set questions real quick. But if there are any follow-up questions, again, feel free to pop them in the chat and I will take a look at them. Okay. There are a lot of questions about problem set 3, 6, and I will go over that in a minute. I'm going to start with problem set 1, 5E. So I'm gonna pull it up. You'll be looking at me, but I'm not looking at me. So forgive me as I read on the screen as I pull up problem set 1, question 5E. And if you are able to do the same thing, please do so. All right, problem set 1. Word is strongly thinking about opening my document. Okay. All right, so problem set 1, question 5, if I recall, is the article where I give you a chart. I wonder if they wrote question 5E. Got it. Okay, so so question So question 5 in problem set 1 is the study of Dahl and Bradford Hill. So I won't open the PDF, but you can do that. I've provided you the PDF of the landmark Dahl and Bradford Hill article, which is one of the first that said that, hey, smoking ain't that good for you. And question E in that, so sub-question E referred to a specific table. Didn't ask you to read the table, but just look at the table and ask you to calculate relative risk and absolute risk difference. Now, my guess is, without opening up the table, that the table probably reported incidence rate and not cumulative incidence. Now, you can measure relative risk on incidence rate, again, because you're just dividing two incidence rates by each other. When you divide two incidence rates by each other, the denominator of person years drops out. But absolute risk difference, as I mentioned before, is a subtraction. And so the units have to stay in. Now, look, I'm not going to nickel and dime you on a test. If you miss the units, as long as you know what you're doing, you'll lose a quarter of a point or something silly. But if you're measuring an absolute risk difference, when the risk is being measured in incidence rate, the absolute risk difference has to be reported in person years or per 1,000 person years or what have you, which is why this with this question 5E was per 1,000 person years, because measuring absolute risk difference when the risk is being measured at incidence rate requires that unit. Relative risk, again, doesn't matter because you're dividing it out. All right, so that's problem set 1. Now let me turn to the cruel and evil problem set 3, question 6. Now first, and I'm going to go over this as much as anybody wants to hear it, but first, suffice to say, this question is way harder than anything I'm going to ask you on the exam, okay? This is beyond the pale in terms of the exam. I was trying to make a point about the issues with sensitivity and specificity. So for those who are worried, like, oh, am I going to ask this in the exam? No. This is the level of math required for this question is beyond the scope of what I'd ask on the exam. The point I'm trying to make in problem 6 is the problem with non-differential bias, right? With non-differential bias, when you mistakenly have people in the wrong group, if it occurs in both directions, it tends to bias things towards the null. So that was the point I was trying to make in problem 6, is if you can calculate odds ratio in problem 6, but let me make sure it's a case control. Yes, it is a case control study. So if I give you a case control study, it would be an odds ratio. And if you then have some misclassification going in both directions, it will tend to bias things towards the null. So that's, if you come away only with that from this question, then you're legit fine. I will briefly talk about the calculations in problem 6, but again, I won't do any better job here than I did on the video. So if you haven't watched my video link to the problem set, which I think was distributed or posted online by Dr. Falls, one of your classmates told me there was an issue with the file being locked. Dr. Falls apologized for that, so it should be unlocked now. So you should now have links to all of the answers for problem set 1 and problem set 3 with a video walkthrough. But quickly looking at 6B in problem set 3, let's assume the information about the prior diagnosis of tuberculosis provided in the chart above is the truth of the situation, meaning that the data I gave you in the 2x2 grid is actually factually correct. You may not have a way of measuring it, but if you could reliably measure it, that 2x2 chart at the beginning of problem 6 in problem set 3 is the factual information, even though you have no way of measuring it, okay? Now, I propose that the way we're going to measure it is using a self-reported questionnaire. Again, I'm reading along with you. And the questionnaire, we know based on extensive research, isn't perfect. It's 90% sensitive and 85% specific. So let's talk about each of these data points individually. So 90% sensitive means that everybody who with the actual finding, only 9 out of 10 of the times are we going to find that finding. The other 1 out of 10 times we're not, okay? So the questionnaire is going to classify prior diagnosis of tuberculosis. I say that again in the stem of the question. So for prior diagnosis of tuberculosis, again, looking at the 2x2 grid, which you can pull up if you'd like, but in the upper left, there are 104 people in the real world, gold standard, 104 people were previously diagnosed with TB and have a resistant status. Of those 104 people, my questionnaire is only going to detect 90% of them accurately, meaning that of that 104 people, 0.9 times 104, about 94, are going to stay in that box. What happens to the other 10? The other 10% of people who I got wrong are going to shift. I'm going to misclassify them as not having had TB in the past. So I'm going to shift them right, again, as the 2x2 grid shows. They're going to stay as resistant to B, but 10 of them have moved over to a no prior diagnosis of TB because I got them wrong, okay? In the lower left hand of that grid, I have 180 people who were previously diagnosed with TB who are susceptible. But again, only 0.9 of them are going to be correctly identified as prior diagnosis of TB by virtue of my suboptimally sensitive questionnaire. So 10% of them, 18, I'm going to get wrong. And how am I going to get them wrong? Again, the questionnaire is measuring prior TB exposure. So I'm going to get them wrong in that metric. 18 of them are going to move from the lower left to the lower right, 18 shift. Now, unfortunately, the questionnaire is also not 100% specific. What does specific mean? It means the people without the prior exposure. So 100% specific means people without prior exposure, I'm going to correctly classify as no prior exposure. Any drop in specificity means people without prior exposure are going to move to the other side. They're going to move to prior exposure. So if my questionnaire is only 85% specific, it means I'm only going to 85% of the time correctly categorize somebody without prior diagnosis of TB. So in the two right-hand boxes, 281 and 2931, both those boxes, 15% of people are going to get wrong and they're going to move left. So 10% of people on the right, on the left move right, 15% of the people on the right move left. And once I make that shift, then I draw the new grid. Okay, so that's where, again, I can, if you pull up my video, you'll see it. But that's where the numbers in this grid in problem 6B come from. So again, I'm happy if anybody wants to email me, I'm happy to give them a more detailed explanation, but the video does go through it way beyond what you need to know. Now, you need to know sensitivity. You do need to know specificity. You should be able to calculate sensitivity and specificity given a grid like this. You should be able to, tell me what's going to happen if a test is not perfectly sensitive. What does it mean it gets wrong? What does it mean if a test is not perfectly specific? What does it get wrong? So you should be able to do those things, but the heavy math load of this question 6B is way beyond the scope of what I would ever ask you to do on an exam, I promise. All right, just looking at the other questions to make sure. I think all of these things are asking the exact same thing. Let me just go through them all quick. That's because the problems that I don't understand the logic, how to fill out the table. Okay, so I think I have all of the questions. I'm not surprised. And again, I apologize, it's a cruel question, but it was intended for a small group and to illustrate a point. Just that, there's a lot of imperfection the way we do things. Okay, so that's the end of the questions I was asked. Let me just do a quick reload of the page. So while I'm finishing up, if there are additional questions that you want me to address, I'll give it another minute or two. Please go ahead and pop them in the live chat, and I will do my bestest to respond to them post haste. And again, I apologize that we started late and then I've gone a little bit past the 7 p.m. time. I do my best to respect your time, and sorry I didn't do a great job today. Oh, I have a couple more questions. Let's take a look. Oh, maybe I do 1, 2, 3, 4, 5, 6. So no, I do not have any more questions as best as I can tell. No. Okay. So that is all the questions that I was proactively asked. Again, giving it another 30 seconds or so just to see if anything pops up. Again, feel free to email me. If something I can't answer easily by email, I'll be happy to give you a ring at the time of your convenience, because sometimes it's just easier to talk through stuff than it is to actually respond. Writing is a very inefficient form of communication. Can I talk a little bit more about the third criterion of confounding, that it is not an intermediary step? And one of the examples in the interactive PowerPoint, there was an example about eating salad. All right, I'm going to pull up the interactive PowerPoint written by my good friend, Dr. Kelly Arps, class of 2016 or some such thing. Maybe not that far ago. I'm sure that there was a time when the eating salad example made a great deal of sense to me. But those were, those were simpler times. All right, PowerPoint opening. Why isn't eating salad, which might have a pathogen, an intermediate to getting foodborne illness? All right, hold on. I believe it is finally opening. I think my computer is using all of its processing power to attempt to live stream. There we go. All right. So let us find this salad analogy. All right. I believe this is on slide for those of you who may be following along at home. Slide number is this. Slide number 8. All right, putting up the PowerPoint now. Oops. There we go. In a foodborne illness outbreak, women are more susceptible to the pathogen than men. So it says that is a possible. Okay, I'm not sure why that would be anything to do with the intermediary step. So is there another salad example in here that I didn't see? Let's see. How much salad can we possibly have? I feel like that's the only salad example. All right, closing of that. So in a foodborne illness outbreak, women are more susceptible to the pathogen than men. So its lists, is it possible that that salad consumption is a confounder? 1 minute. I'll get back to you. I'm going to answer Adam's question. So let's opine for a minute that it is possible that one of two things. One, the salad could be the vector of illness, right? So the intake of salad could be linked. Alternatively, people who eat more salad might eat less of something else, and therefore might be less inclined to get the illness. So it's conceivable that salad would be imbalanced in the outcome group. Is it conceivable that salad is imbalanced in the exposure group? Is it possible that men and women eat different amounts of salad? At the risk of being sexist, I would propose that it probably is. Men, in general, probably I would opine eat less salad than women do. I have no evidence to support that statement, but let's at least agree that it's a possibility. So without any data in hand, I would theorize it's possible there's an imbalance in salad intake between men and women. So that's the exposure, gender. I opine that there may be a difference in terms of foodborne illness. That's the outcome of interest. So based on those two criteria alone, it's possible. Now, why is it not an intermediary? That may be the question you're asking. So, so it doesn't necessarily follow that all men or women eat salad, right? So in getting from men to, or from gender, from sex to foodborne illness, salad, I don't know, is the only way you can get it. Again, the example I use of the intermediary is really carcinoma in situ. It's the only example. The salad example is an odd one. So something that directly precedes the outcome of interest. So lung cancer has to start as a carcinoma in situ. It can't get any other way. That can't be a confounder because it is an intermediary. You can't get to the outcome without going through this exposure. It'd be like saying, is passing the 500-meter mark in a kilometer race a confounder? No, you can't. You can't get to the end without passing the intermediary. So I guess that's why it could be a confounder, because it's conceivable. I guess we don't know enough about the question, but if we knew more about the foodborne illness, and the only way you could get it was by eating salad, and everybody who got the illness got salad, then I guess in that case it could be an intermediary. We just don't have enough information in the stem to make that conclusion. So again, the example I would use is something that must precede the outcome. If something must precede the outcome, it can't be a confounder. Again, passing the 500-meter mark at a kilometer race, having a carcinoma inside you before developing frank cancer. All right. For setting up 2x2 tables for cohort case control studies, relative risk / odds ratio. Does it matter if we set an outcome exposure on the left top? Is it different for each? Now, you can set that. My pleasure, Adam. You can set that up however you'd like. Whatever is easiest for you. I think it's most common, just from a readability standpoint, to put the exposure on the left and the outcome on the top. But I don't much care. As long as I'm not going to judge you for setting up grids. You do you. As long as it's clearly labeled what you intend, there's no right or wrong answer. So you can set up exposure and outcome wherever you want, as long as they're adequately labeled. I think it's fine. And the same is probably true in the literature. I don't know that it's strongly recommended one way or the other in the literature. Is it correct to say that increasing specificity moves some false positives to true negatives, and increasing sensitivity moves some false negatives to true positives? All right. So I got to digest that one. I'm not as smart as I used to be. All right. So increasing specificity means you're more likely to identify negatives correctly. So if you increase specificity, you are less likely to have right. So false positives, people who are negative, but you call wrong. So they don't exist. In a 100% specific test, you have no false positives. So I do think it's correct to say that increasing specificity moves from false positives to true negatives. I agree with the first part of that statement. Second part, increasing sensitivity moves from false negatives to true positives. I agree with that as well. Sensitivity is only germane to positives, right? So it only is pertinent to positives. People who are true positives are either people who are positives in real life are either true positives because you detected them correctly, or false negatives because you detected them incorrectly. As you increase test sensitivity, you definitely transfer people from the false negative back into the true positive group. So I agree with both portions of your statement. All right. So I've addressed Adam's question. Snafu, that's a lovely name. I assume it's not your real name, and I've addressed Zoe's question. So I think we'll call it quits there. Again, I apologize for the technical difficulty, but we'll do better in the future. I will remain available for questions. Good luck on your test on Friday. You're all good. Oh wait, last question from Miley. But for those of you who want to check out, again, apologies. Thanks for coming. I'll be available by email to answer any questions you have. Lastly, Miley, if I'm pronouncing your name correctly, I apologize. You're welcome. If not, I apologize. Can you please clarify significance as it relates to confidence interval? I got a little lost in your explanation earlier. It was probably a quick explanation with my rapid New Jersey rate of speaking, so I apologize. And yes, happy to go through it again. So 95% confidence interval is defined as if I repeat the same study 100 times, 95 times out of 100, I'm going to get a result in that 95% confidence interval range. So that's how it's defined. Conveniently, and there's a mathiness to it, it's also true that if my 95% confidence interval does not include the null, meaning a relative risk of 1 or an absolute risk difference of 0, if my 95% confidence interval does not include the null, it is a statistically significant result at a p-value of 0.05. Okay, so once again, if my 95% confidence interval on my study result does not include the null hypothesis, relative risk of 1, it means that my study is statistically significant at a p-value of 0.05, meaning the p-value of the study is necessarily less than 0.05. So you can figure out if a result is statistically significant in one of two ways. One, I can tell you the p-value. That makes it easy. Or two, I can show you the 95% confidence interval. And as long as your p-value of interest is 0.05, if my 95% confidence interval doesn't include the null, the result is going to be statistically significant at a p-value of 0.05. So that is the answer to that question. All right. Well, there's still 21 of you stalwarts sticking around. I hope I did not disappoint. My pleasure. Again, be good. Have a great week and email me any questions you have. Apologies again. Schulman out.